Good evening. My name is Evo Farage. Today I'm going to present the historic advancements of wind standard and building codes. This topic is very important because wind is one of the most destructive forces the build faces, especially in places like coastal areas, the Caribbean, and as part of the United States, such as Florida. Over time, our understanding of wind behavior has evolved dramatically, and the building codes we use today have been shaped by decades of research, failures, and lessons learned after major storms. When we talk about wind hazards, we're not just talking about hurricanes. There are actually several different types of storms, each creating a unique wind pattern and type of structural stress. Tropical cyclones, like hurricanes, produce sustained winds, intense gusts, and a storm surge, making them extremely dangerous in coastal areas. As picture one that we have there is Hurricane Katrina. The mid-latitude cyclones and nor'easters produce long-duration winds, which can fatigue structures over time. Even if the wind speeds are lower, the long exposure can create cumulative damage. Tornadoes, as picture number 2 that we have on the slide, are completely different hazards, generating destructive localized gusts that can exceed the 200 miles per hour. And then we have downburst and derechos is the picture number 3. Actually, that picture shows derechos because downburst is one of those lines, and the combination of all those lines called downburst is that combination is that we call derechos. These derechos can create straight line winds that can push entire structural walls inward or outward. It's also important to emphasize that wind vulnerability depends heavily on geography, terrain, and exposure. For example, a coastal home in Florida faces extremely different wind demands compared to a building in the middle of the country. That's due essentially one is the exposure, and the other one is that, of course, the wind hit with less impact because the wind loses velocity and potential forces from friction forces with other structures or the terrain itself. The combined wind and flood hazards, like a storm surge plus high winds, make coastal regions especially vulnerable. Like I explained previously, the coastal regions are the more impacted by this kind of phenomena. When a building fails during a wind event, it usually doesn't happen all at once. It often starts with small weaknesses in the building envelope or tiny connection failures. For example, the one that we show there is the connection of roof to walls. Is very typical here in the United States, since a lot of the houses here are wood and are not like concrete. It's not the roof is not concrete, so that kind of connection suffer a lot from this kind of either tornadoes or hurricanes. Like I explained previously, the roof to wall connection is one of the most critical areas. If the roof begins to lift, even slightly, internal pressure builds up, which makes the roof blow up even faster. Another common failure is with components and cladding, such as windows, doors, and siding. Once a window breaks, the internal pressure skyrockets, and the entire building becomes significantly more vulnerable. We also see failures a wall to foundation connections, especially in order or lightly reinforced structures. Non-structural elements like signs, HVAC units, and even roof tiles can turn into airborne debris. In coastal regions, foundation score and also weaken support, making the structure more likely to fail under wind loads. All of this lesson taught engineers that the building envelope must remain intact to protect the structures. Historically, post-disaster investigations have been incredibly important. After every major hurricane, Andrew, for example, in 1992, Charlie in 2004, Katrina in 2005, or Michael in 2018, we learned something new about wind behavior and structural deficiencies. For example, after Hurricane Andrew, we discovered widespread failures in roof sheathing, attachment, and inadequate wall anchorage. After Hurricane Katrina, we realized that many buildings were not prepared for combined surge and wind effects. Or another example is with Hurricane Michael, failures highlighted the need for a stronger connection even in newer buildings. Wind tunnel testing and modern forensic engineering help provide more accurate local pressures. A big takeaway from all these events is that small construction details make a huge difference. Even something as minor as the spacing of nails or a strength on a strap can determine whether a roof stays on or gets ripped away. Those small details make a big, huge difference when we are designing or constructing houses here in the United States. Historical development of wind design provisions. Before the 1970s, wind design relied almost completely on empirical formulas. Essentially, engineers used very simplified pressure coefficients that didn't account for gust and exposure difference. Then the ANSI A58.1 became one of the earliest national load standards. However, it still lacked gust representation and didn't distinguish between open terrain, suburban terrain, or dense urban exposure. A major milestone came with ASCE 71995, which introduced the 3-second gust wind speed. This was the major shift because instead of designing for average wind speed, we started designing for realistic peak gusts that cause actual structural damage. This transition made wind load calculation far more accurate and significantly improved safety. Here we see a representation of all the disasters that had made our codes to change. For example, we have the first one, Andrew, we have Ivan, we have Katrina, Sandy, Irma, Maria. All those phenomena has made our codes change in either way. This representation is not only, this picture is not only about wind, it's also about flooding and other kind of designing issues that we have been facing with these phenomena. But this is an interesting timeline of how those phenomena has made our codes change. Has made our code to change during the over time. The ASCE 7 continued to involve and refine wind design provisions. One key development was separating the main system that received wind loads from component and cladding, which experienced much higher localized pressures. Later editions, such as the ASCE 716 and 722, refined exposure categories, updated wind maps, and incorporated new research from boundary layers and wind tunnels. Other organizations like the ASTM, ANSI, or ICC, and SPRI contributed material specific standards for these things like roofing, membranes, anchors, and impact-resistant glazing. Another major development was performance-based wing design, which allows engineers to customize solutions for unique or complex buildings rather than relying solely on prescriptive code requirements. There we have picture of the IBC, International Building Code, the ASC 722 is the latest one, the latest version is the same one that I use at work when designing buildings. And the Florida Building Code, of course, for us that we live in Florida, that's everything that we design at work, any shear wall or slab deflections, all that, wall deflection, columns, all that are based on the Florida Building Code. But on the wing standards, that code, also the IBC code, they refer as the AC code for like the wing, for wing loads and wing standard, how do you say, wing standard designing, they always refer to the AC as it's like the mother of the wing is for designing. The International Building Code is updated on a 3-year cycle and reference, as I said previously, the ASCE 7 as the national standard for structural loads, including wind. At least at work, what we do is essentially other loads, but essentially for wind, we use the ASCE. The major turning point in U.S. construction was the Hurricane Andrew, after which the Florida Building Code was completely redesigned. Florida now has some of the strictest wind resistance requirements in the world, including impact-resistant glazing in high-velocity hurricane zones. Other coastal states enforce higher design, wind speeds, and debris protection requirements. But globally, wind codes vary significantly. Some countries use different gust duration, different exposure classification, or different wind return periods. For example, Canada, they uses, I think, a 1 hour average period for what I think is incorrect, because in 1 average 1 hour average period is like designing as previous codes. You are losing the gust effect of the wind, and you are not designing for the highest peak on the wind forces. Even also in Texas, they use, I think, they use different timing than here in Florida. Even though codes improve every cycle, one challenge is that adoption and reinforcement are not always consistent, as I said previously with these two examples. Many regions lag behind, and older buildings remain highly vulnerable. The future of wind design is shifting toward digital and performance-based approaches. CFD, computational fluid dynamics, and aeroelastic simulation allow engineers to model wind flow around buildings with far more detail than traditional methods. Digital twins, which use real-time sensor data from actual buildings, help refine wind maps and improve long-term performance predictions. These digital twins, what they do is they simulate the reality into computer systems to have an idea, like a real data that they can use for designing. Climate change is another major factor. For example, as a storm intensity and frequency shift, hazard maps will need to update more frequently. Probabilistic wind hazard mapping will help account for uncertainty and long-term risk. We are also seeing a stronger focus on resilience, meaning buildings designed not just to avoid collapse, but to stay functional and allow rapid reoccupancy after a storm. And of course, sustainability is becoming increasingly important. So future standards will balance carbon reduction with structural safety. And as a conclusion, we conclude that wind standards have evolved, have developed dramatically from simple empirical formulas to highly advanced research-driven, performance-based systems. Each major storm has contributed lessons that shape today's codes. Modern tools like CFD and digital twins will continue pushing design forward. However, challenges remain, especially in updating hazard maps, improving tornadoes modeling, and ensuring consistent enforcement. Overall, the evolution of wind standards reflects a continuous effort to improve safety, resilience, and adaptability in the face of increasing wind-related risk. And also, I want to show the reference that we use for this, that I use for this topic. These are the key reference used to support the information presented. They included the ASC standards, academic journals, and research studies related to wind design and building code development. Thanks a lot, and hope to see you soon.